Hi everyone, my name is Farid Zidat. I am Senior Application Engineer within Altair. Today I'm going to speak about magnetic force computation with Altair Flux. So this is the same philosophy in 2D and 3D. This example is a permanent magnet machine. The first point I want to mention here is magnetic force using virtual work method. So then using the sensors. To use the virtual work method, it's mandatory to have the region considered totally surrounded by air or vacuum. In my case, I will compute the magnetic force on the tool and the magnetic force on the magnet. So that's why I am using air gap parasitic region. This is some configuration we can find in some rotating machine actually. So this air gap line region will allow me to take into account the air gap without displaying the geometry of the air gap. And I can put like a width of the air gap here is 0.05 millimeter. The same thing for the glue in the air gap, in the magnets. I put the same air gap and I am using line region. So here for the tooth, it's also surrounded by the coils, which is the copper with mu air, permeability mu air equal to 1. So it's from magnetic point of view, it's like air or vacuum. And then I have the wedge with permeability mu air equal to 1, and then the air gap. And then the air externally. So the tooth here is considered as surrounded by air or vacuum. Something you have to activate in advanced mode. Go to options, user mode, and then activate advanced mode in order to be able to use line air gap region, and then Flux will consider this region, for instance, totally surrounded by air or vacuum. If you want to stay in the standard mode, then you have to display the real air gap each time. And this is okay in 2D, but it can be time consuming in 3D because the model will be heavier. Right, so the forces are computed after the solving in the post-processing side. Then it's possible with Flux to define your sensors. So I can define a sensor on the magnet with predefined type of sensor of magnetic force, and then define the force on the tooth with a predefined sensor also. Once I define the sensors now before the solving, I can solve the project and so on. So when the project is solved, I can go to the sensors and right click, display curve here on the magnet. So I have the component module in blue, component 1, which is X component of the force, green is the Y component of the force, and Z component in yellow. In 2D it's 0. The same thing, right click on the sensor of the tooth, display the curve, and I can see the curve of the force module, X component, Y component, and Z component of the force. Now this is for the force using virtual work method, but there is other method using Maxwell Tensor and magnetic pressure. So Maxwell Tensor is explained here in the help. So it's through the IO context. I will open it now. It is computing the magnetic pressure from the flux density on the air gap, radial component, tangential component of the magnetic pressure. Then we can compute the magnetic force on the tooth by projecting this magnetic pressure on the support on the tooth in order to compute the magnetic force. Then we can compute the magnetic force per tooth, global, or magnetic force per nodes of the mesh support we created on the footprint of the tooth. The second method is using magnetic pressure or depth mag ds, and the force here is mandatory to be on the border of a magnetic region, typically the stator, and we are going to compute the normal component of this force through the magnetic pressure, and that's why it's always perpendicular to the support we are considering, right? Today I am going to speak mainly on the Maxwell Tensor method. So let's see this Maxwell Tensor method, how it is. Okay, so let's come back to our project and go to the data exchange, open data import export context for mechanical coupling. Then we are going to enter to dedicated context. I am going to make my support invisible. Okay, so I have like a 3D one. So this is the support I can create for Maxwell Tensor. It's mandatory to be a pure cylinder here to use a simplified projective method. There is another method using the same Maxwell Tensor, but it's called a generalized projective method. So let's talk about this Maxwell Tensor method. First of all, I have to create the support that is on the inner footprint of the stator tooth. So new. Then I have to use support defined by surface quantities. I can use support defined by import mesh if I want, if I have a mesh done by SimLab or HyperMesh. I will create it here in Flux for now. So I will make defined by a set of lines. Then I will use selection by relation. So first of all, I am going to select all the lines of the stator tooth. Then I have possibility now to make selection by region again. So select all air gap stator. Sorry, only air gap stator, and make intersection. Then I have selected all of them. I will extrude it and use 4 layers, and I will rebuild the device. Okay, so this is the one I create now. I can make it set visible. No, it's not this one, sorry. So this one. Okay, and now I can compute the force on this support from Maxwell Tensor. Then again, the Maxwell Tensor will compute the magnetic pressure on the air gap from the component of the flux density. Then we are going to project this this magnetic pressure on the support mesh in order to compute these forces. Once the support is created, I can go to the force data collection and make new. And here I am using the simplified projective method. Please have a look on the help to understand what is the generalized projective method and the direct method. I am not going to speak about them today. Then I am going to select the support I created, make the collection of the force or the computation of the force for a specified interval. Here I am going to select one electric period from 72 to 144. Okay, then I can go back, right click, and make collect data. Alright, then once the data collection is done, I can now visualize the time evolution of the forces. First of all, I am going to show the forces, the row of the forces. And it's decomposed on radial and tangential. I will show first the resulting force. Okay. I can show the radial and I can show the tangential. What I can do also is to show the resulting, but the global force. And once I show the global force per tooth, like this, I can then go to the data visualizer and visualize the curve, right? For instance, I am going to select this group, which is the tooth, one here. And because I evaluated the force from 72 to 144, I have to select the same interval. And then I can see my force evolution. This is not XYZ component, but it's a radial component, tangential component, and the module, and Z component, of course. But yeah, we have not a big difference between XY component and the radial component here. So it's almost the same. But someone can imagine that the force computed here will not be the same. If I go to the data visualizer again and standard evolution, maybe I can select this one, or maybe the third one, or maybe the fourth, number one. Okay, and then select the interval 72 to 140. Okay, it's almost the same thing, but yeah, we have a few differences, but yeah, it's something we can check like this. And this is it for the magnetic forces computation, a temporal evolution. Now, if I want to have the harmonics, it's also possible. Then I have to go to derivative, make new, and make the FFT on data collection 3 for one electrical period. It's mandatory to select one electric period or half of electric period. If you selected half, then you can use duplication and it will duplicate the signal automatically, and make OK. And then go back on your derivative, collect data. So once the data is collected, then you can go again to data visualizer, and in this case we are going to visualize the harmonics and not the temporal evolution. So let's visualize the harmonics and the harmonic number 10, and as you can see, I can always use decomposed in radial and tangential component. Let's see the resulting one. Okay, and then here I can vary the phase. Maybe I can decrease the here, and we can vary the phase of the forces. I can make the same thing now the global and show the 10th. And I can also vary here. The same thing, once you visualize the global arrows, you can go to the curves and visualize the harmonics again of the force on here. Let's select 30 harmonics to visualize on the curve. So we have DC component and the harmonics here of the force. All right. So this is all what we have for the magnetic forces using Maxwell Tensor. Then in the same context, you can use dfMagDS if you want. And here you can go to data export and export as a Masterman format or a data file format from tabulated one to use these forces in your structural mechanical analysis tool. This is all what I have for magnetic forces. I prepared also a small example in order to show the Laplace forces. So the Laplace forces here I choose to show them on the coils. So here I displayed only a few wires on a given coil in order to see Laplace force behavior on these coils. So once the project is solved again, I have to go to the data exchange and open data import, export context, and then go to the mechanical coupling. Okay, so let me again make this one invisible. The same thing, I have to create a support where I have to compute the forces. So I have to go data support, new click, right click, new support, and in this time I am going to select the support defined by volumic because I am going to compute the Laplace forces, and the Laplace forces are volumic, are not and not surfacic. So I have to define the set of faces I am going to extrude, right? I will say yes, I will put 4 layers, and I will not duplicate, so I will build only for this group. Okay, so it's created, I can make it visible, and it's in 3D, right? Then I can go to force data collection, right click, new. This time I am not going to use a Maxwell Tensor, which is the projective method, but I am going to use a direct method for volumes force, which is dflap v, which is Laplace forces here. And I am going to select my support, and you can see here there are some integration method or computational method. Again, please have a look on the help for more information. I will select an interval which corresponds to an electrical period again. Okay, so when you create the support, you have to go again on it, right click and collect data. Okay, then once the data collected, I can visualize, like for the magnetic force, I can visualize the temporal evolution, but first let's see now the forces, the Laplace forces at node. So here they are not decomposed in radial and tangential, but they are expressed in the global coordinate system. I can select then my force data collection. First of all, I will show them on the nodes. Okay. Then this is for a given time step. I can show them on the global, but again they are expressed on the global coordinate system, which is Cartesian. And now I can, once I have the global one, I can show the temporal evolution of the forces. Then once the temporal evolution of these forces are computed, we can also compute, let's say, the harmonics. So we can go to the derivative, make new, and then we can select collection of the forces, always on one period electric. We can make automatic duplication. It's useful when you have half of a period electric. Then you can make OK and go back, right click on it, data collection. Once the data is collected, now you can make data visualization of the harmonics, make new. I can make it always expressed on the global Cartesian here. Then I will show the harmonic number 10, for instance. And here I can really vary the phase. I can show also the global one. Okay. So you can see the Laplace force behavior, and I can show now the harmonics of uh, this one, for instance. And we can see the evolution of the forces here. So this is all what I have to show you today, how to compute the magnetic forces with a few methods we have in Flux, and how to compute Laplace forces also. Thanks for your attention, and please feel free to ask your question if you have any.